Good day, everyone. Welcome to another lecture on this lecture series related to machine learning. And in this particular lecture, we will be discussing about the regularization. So you can see that in our last lecture, we said that if we have a simple model, this simple model results in underfitting. And if we have a complex model, or we can say higher degree polynomial, okay, and in this higher degree polynomial it performs well, but it has the issue of overfitting. So that means this particular model has less bias, lower bias, okay, because it is performing well on the training data, but it has high variance. This we have already discussed in our last lecture. So what we are going to do, we will use this complex model because our aim is lower bias and low variance. So we will use this complex model, but we will try to decrease its variance. And how we can decrease its variance? We can decrease its variance if we make it as higher degree input, or we can say the parameters associated with higher degree input as very small. We will make them very small. For example, if we are saying that our model is like this, hypothesis model is like this: x2 x square plus x cube plus. So for higher degree polynomials, for example, for x raised power 4, for x raised power 3, we will make these parameters which are associated with these higher degree inputs, we will try to make these as small as possible. And by making these small, what we are doing, we are making this hypothesis function less sensitive to data variations. Okay, that means we were having a higher complex model means that it was having lower bias, but the disadvantage of this complex model was high variance, and we have decreased this variance. And how we have decreased the variance? We have decreased it by penalizing these higher order parameters. Okay, and how we are penalizing this? We are penalizing this by having a new loss function. Okay, it is written like this. So our actual loss function was j theta, and to this j theta we will add another thing, that is r theta. Okay, so this is a constant, and it is also called a regularization parameter, regularization parameter, regularization factor. Okay, so we are adding to this loss another term, this particular term. So this r theta is a function of theta, and we have a new cost. So then this new cost is called regularized loss. Now instead of decreasing j theta, we will decrease this particular quantity, and decreasing this particular quantity means decreasing this and decreasing r theta. So this portion we already know. Decreasing j theta means having a model which has lower bias, And decreasing r theta here, we want to decrease r theta in such a way such that the higher order theta parameters will become small. So this r theta will be the function of theta. Okay, so let me write again here. What is the regularized loss? The regularized loss is j theta equal to original cost plus regularized parameter into r theta. Okay, this r theta is also called a regularizer. Now this r theta, there are different mechanisms of choosing r theta. The first kind of regularization is called ridge regularization. In ridge regularization, this r theta is equal to this r theta that we are using. This is equal to summation I running from 1 to n theta I square. Okay, so the new cost will be j theta lambda is equal to j theta plus lambda times summation I running from 1 to n theta I square. So we were having how many parameters? N parameters, theta 0, theta 1, dash 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 theta n. But we are only adding from these parameters. So that means we are regularizing these parameters. We are not regularizing theta 0. So you have to keep this in mind. So regularizing this means, or we can say we have to decrease the cost. So decreasing the cost means we have to decrease this and we have to decrease this. And this term will be decreased only if we decrease the theta i's. Okay, and by decreasing the theta i's, we will be making most of the higher order thetas as very small. Okay, by making these very small, the new theta parameters that we will get, those theta parameters will give us a hypothesis function, and this hypothesis function will be very less sensitive to data variations. Or we can say this particular model hypothesis function will have low variance. So we are able to create a model that has low variance and low bias. So this is one kind of regularization, and this ridge regularization is also called L2 regularization. Okay, so because it is an L2 norm. Now, apart from ridge regularization, there is another kind of regularization which is called, second is Lasso regularization. Okay, so it is also, we can say this Lasso is least absolute shrinkage and selection operator. So in Lasso regularization, this r theta is equal to summation I running from 1 to n mod of theta I. So this was theta I square, and this is the absolute value of theta I. So this is also called a L1 regularization. Okay, so our new cost will be j of theta, regularized cost will be j of theta plus lambda times summation theta I, where I running from 1 to n. But you have to keep in mind we are not regularizing theta 0. So this one you have to keep in mind. The difference between the lasso and ridge regularization is that this ridge regularization makes the parameters small. Okay, their value is very small. And lasso regularization, it makes most of the parameters as 0. Okay, so that means this regularization gives us sparse parameters. Sparse parameters means the matrix of parameters where most of the parameters are 0. Okay, that is the main difference between ridge regularization and lasso regularization. So these are the two mechanisms by which you can regulate the data, or you can do the data regularization. However, apart from these penalizing the parameters, so here we are penalizing, or we can say penalizing the parameters. But there are some other techniques also where we don't have to penalize the parameters. For example, there is a technique called dropout, another technique called data augmentation. Okay, and another technique is uh, early stopping. So these are, and many more are there. These are other mechanisms of doing regularization. Okay, but these methods, for example, dropout, data augmentation, they are mostly used in neural networks, and we will discuss these when we will be discussing about the neural networks. But this early stopping, we will discuss it here. What is early stopping? So let me discuss early stopping here. So early stopping is a method of regularizing gradient descent. Our mechanism linear regression. So this is a mechanism of regularizing linear regression, or we can say gradient descent. So here we don't add any cost function or anything. What we are going to do in this particular mechanism, when we are training data, when we are training our model, so you know that in while training a model, we are doing the we are optimizing theta by repeatedly decreasing j theta. Repeatedly decreasing j theta. So how many times we are doing it? We are doing it till there is no further change in j theta. So this is a loss on training. So this is also called training error. Okay. So we go on decreasing, or we can say we go on changing the theta till we reach to the minimum j theta. Okay, but what we are doing when we are running one iteration, one updation, then another updation, then another updation, each updation, or we can say each iteration is called an epoch. So we have to run multiple epochs. In early stopping, what it is saying, that when you are updating theta, so let's suppose I have updated theta. Let's say I have completed 300 epochs. I am updating this theta. Now again I am updating, and I will check that my j theta is decreasing, continuously decreasing. Okay, or we can say training error is decreasing. Now after some epochs, I will also check the validation error, because validation error will also decrease. However, after some time, this validation error will reach to a minimum, and then again start increasing. Increasing means that now there is high validation error. So that means our model is now overfitting. So we will stop there where we can see that now the validation error is increasing. So that means we have reached to the minimum. Now validation error will increase. It will result in overfitting. So we will stop at this particular point, at this minimum, and the parameters at that particular point will be our optimal parameters and regularized parameters. Okay, so let me make you understand with the help of a graph. So let's say this is our graph. So these are our epochs. Epochs also means iterations. Okay, this is our mean square error here. So our, we know that by running more and more epochs, our training error will decrease. So this training error will go on decreasing. Training error will decrease. But also when we are doing the iterations, after some time we will also check the validation error. The validation error will also decrease in multiple iterations. One time it will reach to the minimum and then it will start increasing again. So this means now we are overfitting. So whenever we have checked that we have reached to the minimum and now the validation error is increasing, we will stop here. So the parameters at this particular point, or we can say the hypothesis function at this particular point, will be our best model. So this will be a model you can see with low training error and with low validation error, means with low bias and low variance. So this model we will choose and we will use this model. So here we don't have to do any penalization or anything. We directly did some trick which is also called early stopping. We are stopping earlier. So this is early stopping. And this early stop gives us the parameters which are the parameters of a best model. Okay, so this was all about the regularization. Now as I said that there are other mechanisms also. For example, as I have discussed here, that dropout is one mechanism, data augmentation. These mechanisms we will be discussing in neural network. So one last topic related to the linear regression and gradient descent is that now this was one mechanism of doing regularization. Okay, using an early stopping criteria. But there is another method, or we can say there is another algorithm which neither overfits nor underfits. Okay, or we can say that is also a kind of regularized model, and that is locally weighted linear regression. Okay, locally weighted linear regression. We have seen that if we have insufficient parameters means if we have a simple model, means the parameters are very less, then this results in underfitting. And if we have excessive features, excessive parameters, then it results in overfitting. So we can see from these two that choice of parameters or choice of features is important for better performance. Okay, choice of features is important for better performance. But what locally weighted linear regression does, so it is also written like this: it makes the model, the machine learning model, independent of the choice of features. Okay, what does that mean? I will make you understand. So let's suppose it is not doing any training. So locally weighted regression does no training initially. So there is no training. So what this particular model or this particular algorithm does, let's suppose we have to we have some, so we have a data set. So this is our data set, x and y. So this is input, this is output. Now we have some data point x which is unknown. Okay, and I have to make a prediction for this data y hat, for this unknown data. What linear regression does, what we are other model is doing, other model is we are first finding an hypothesis function by mapping x and y, actual input and output. Then it was using hypothesis function to find an output for an unknown input. But what locally weighted linear regression does, that it modifies this x. Okay, what is the meaning of modifies x? Now it finds the points in x, finds the points in x which are close to this small x. Small x means our unknown data point. Okay, close to x means that now it will make a prediction for this x based on those points, and for the other points which are far from this x, so those points it will neglect, or we can say it will find the points in x and it will give them more weight, or we can say it will add a weight to those points, some weight. Let's suppose it will do a multiplication by 10 to those points which are close to x, and the points which are far from x. Okay, and the points far from x, it will give them less weight. Less weight means that it will multiply them by, for example, 0.1 or something like that. Okay, so these points will be less efficient, or we can say these points will have less effect on the final prediction, and the nearest points will have more, uh, we can say more effect on the final prediction. Okay, then it is going to do, what we are doing, we were trying to minimize initially, or we can say previously we were minimizing this I running from 1 to m h of theta x minus yi whole square. Now instead we will minimize this particular formula I running from 1 to m wi into h theta xi minus yi whole square, and this wi is the weight. And for points which are near to x, the weight of those points will be high, and which are far from x, the weight of those points will be very less. And by finding a theta by this particular mechanism, we will be able to get the best prediction. Okay, however, what is the disadvantage of this locally weighted linear regression? The disadvantage is that for every time we want to make a prediction, we have to minimize the j theta, because every time we have a new data point, we have to modify this x, by giving more weights to the points which are near to x and by giving less weight to the points which are far from x. Okay, so this was one algorithm, or we can say one version of this linear regression that is very less sensitive to the choice of features, or we can say it makes itself independent to the choice of features. Fine. Now, one last thing that we have to discuss related to the linear regression is the model selection. So this is the last topic of this particular topic, model selection via cross validation. What does that mean? I will make you understand. So basically, let's suppose we have multiple models M1, M2, dash 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 Mn. So these are, or MD. These are my models. Models for prediction for some data set. Okay. Now, if I have to choose one among these models, so which one should be the best model, or which, why I can say what will be my choice. Okay. So there are different options available. So option one is, so we will here assume that S is our data set. So this is our data set. Option one will be train each model each model on S on this data set and find the training error of each model. Okay, so we will find the training error of each model, then choose the model choose the model which has lowest training error. So this is one option. Okay, but the limitation of this option is this particular, if we do like this, so we are choosing the model which has lowest training error, but there is a possibility that we have find out a model which overfits. Okay, so the limitation of option one is that we may choose a model that will result in overfitting. So this option is not correct. So what is option two? So let's go with option two, or this option is also called a simple cross validation, or it is also called holdout mechanism. So S was our data set. Okay, we will divide this S into two parts. So one part will be called S training. So we have divided this data set into two parts. One part of the data set is called S training and another part is called S validation. So this part is usually 30% of the actual data set, and this is 70%. Okay. So now from one data set we have created two data sets. One is the training data set, another is also called a test data set or validation data set. Okay. Then what we are going to do, we will train each MI on this training data set, S train. We will train each model on this. Okay. And then we will find the error of each model, each trained model. Okay, so you have to remember each trained model on S validation on this data set, and the model which gives least error, we will choose that particular model, will be the best model. Okay, so what in cross validation we are dividing the data set into two different data sets. One is training data set, another is validation. We will train each model on this training data set, then we will find the error of each trained model on this validation data set. So this remains unknown for each model, and then we will see how it is performing on this unknown data. Okay, and the least error model will be our best model. This is called simple cross validation, or also called holdout. Holdout means that some portion from this data set is not used for training, this is only used for validation. So holding out this 30% of data from the actual data set is the limitation of this particular option as well. So how is it a limitation? Is that when we are keeping this 30% only for validation, okay, that means we are not using this data for training. So we are losing nearly 30% of the information in training. Okay, so that is the limitation of this particular option. Okay, so now to remove this limitation, there is an option 3, which is also called k-fold cross validation. And how this k-fold cross validation works is that it divides this data set into k subsets, s1, s2 dash 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 up to sk. So these are k data sets. Okay, then for each model, mi, okay, what this mechanism does, that for j is equal to 1 to k, it first forms a new data set, and this new data set is equal to s1 union s2 dash 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 s j minus 1 union s j plus 1 dash 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 s k. So it is making a data set of all the subsets except this j. So first it will make j is 1, so s1 won't be included, then s2 won't be included. Okay, so it will train mi on s new, then it will find error of trained mi on sj. So for example, the first j was 1, so s was not included. So it will train model on all the training examples, excluding those which are in s1. Okay, then it will test the model on this s1. Okay, and it will find error of trained mi on sj. Okay, then it will again do the same thing. So it will get how many errors? It will get total k errors, this model mi. Then it will find the average of these errors, average of these k errors. Okay, so first it will do it for m1, then for m2, then for m3, and the model which has the least average error, that particular model is the best model. So this is k-fold cross validation. So you can see that we are using the entire data set, we are not leaving anything. Yes, for every iteration we are leaving one part, but in the next iteration we are including that part and leaving another part. Okay, so this is called k-fold cross validation, and this is the best mechanism for choosing the best model, the model which gives us the least average error. So with this we will stop this particular video lecture here, and as you can see that in this particular lecture we discussed about the regularization, Okay, and for this regularization we discussed two types of regularizing using penalizing the parameters. One was ridge regularization, which is also called L2. Another was lasso regularization, which is also called L1. As I said, that apart from ridge and lasso, there are other mechanisms of doing regularization. One was mm, one mechanism was data augmentation, and another mechanism was dropout, and the third one was early stopping. We discussed the early stopping, and other two will be discussed in neural networks. And then we discussed the cross validation for model selection. And one best cross validation is k-fold cross validation. So let's stop this particular video lecture here. We will meet again in the next lecture with a new topic. Till then, goodbye.